Hi, my name is Arad from the University of Greenwich, and today we are diving into the world of wireless communication to understand why Wi-Fi or WLAN and Zigbee sometimes interfere with each other, although they're different technologies. And later on, we will try to classify these signals in MATLAB using semantic segmentation based on their spectrogram. And overall, this project is as part of the MathWorks AI challenge on radio frequency signal classification using artificial intelligence. Zigbee is a low-power, low-data rate wireless standard mainly used for smart home devices like smart bulbs, sensors, and security systems. It's designed to run on small batteries and connect many devices in a mesh network. Wi-Fi, also called WLAN, is the wireless technology that lets your phone, laptop, or smart TV connect to the internet. It's designed for high data rates and longer range, often streaming videos or downloading files. Both Wi-Fi and Zigbee operate mostly in the 2.4 GHz industrial, scientific, and medical or ISM band, a free-to-use part of the radio spectrum, and that causes them to overlap or interfere with each other. Here's the thing, Wi-Fi signals are much stronger. They transmit at higher power and over a wider bandwidth. Zigbee signals are weaker and narrower but can be overwhelmed if a Wi-Fi device is nearby on overlapping channels. When Wi-Fi and Zigbee signals overlap, Zigbee packets might get lost or delayed, causing smart home devices to respond slowly or disconnect. It's like being in a crowded room where Wi-Fi is shouting and Zigbee is whispering. WLAN follows the standard 802.11 and it occupies channels 1 to 14. The bandwidth of each channel is 20 MHz, each channel is 5 MHz apart, and channel 1 starts at 2412 MHz. Now, here is this demo shows channel 1 of WLAN, and as we said, it's centered at 2412 megahertz, and it goes 10 megahertz to the right side and 10 megahertz to the left side, which in total will be 20 megahertz, and that's the bandwidth we mentioned earlier. The middle part of channel 1 is called is where the data subcarriers are, and it goes up to its absolute power goes up to 15 to 23 decibels. And if we take a look at this chart here, so the further we get from the center, so if we get 10 megahertz away, 10 to 11 megahertz away from the center, the max power relative to the peak drops by 20 decibels. So if we have, for example, a 20 decibel peak in here, after getting away 10 megahertz from the center frequency, it will drop down to almost zero, meaning that most of the data and most of the signal, most of the power in the signal is transmitted through this 20 megahertz range, and that's where our focus is going to be. Now, I mentioned that each channel is 5 megahertz apart. Here I have shown the channel 1 and channel 2 of WLAN, and as we said, channel 1 has a center frequency of 2412 megahertz, and if we add 5 to it, so 5 megahertz away, it will be channel 2, which has a center frequency of 2417 megahertz, so which is here, and it has the same shape as channel 1, but the thing is that there is a lot of interference in here, and that is not what we want within the WLAN itself. And actually, if you take a look at all of the channels, so channel 1 to 14 of WLAN, you can see that there is a lot of interference in between. But there is a thing, so if we take a look at non-overlapping WLAN channels, which are channel 1, channel 6, and channel 11, and why do I say non-overlapping? Because if you take a look at them, so channel 1 here, channel 6 here, and channel 11, there is a gap between them and they do not interfere with each other. And they are very popular because they avoid interference within WLAN itself. They are very popular WLAN channels. Now let's move on to Zigbee. It follows the standard 802.15.4 and it occupies channels 11 to 26 within the standard. Now, channels in Zigbee in this standard do not correspond to channel in WLAN because they follow two different standards. Now, each channel in Zigbee is again 5 megahertz apart and they each occupy 2 megahertz of bandwidth, and that 2 megahertz carries most of the signal's energy, and usually in presentations and graphs they show it as 4 megahertz to include side lobes. Now, we said that it starts from channel 11 to 26 within the standard. So channel 11 has a center frequency of 2405 megahertz and it's represented here. And so in this picture we have our WLAN channels again, so channel 1, 6, and 11, which we said they are very popular because they do not interfere with each other within WLAN itself. And we have Zigbee channels, which are the pink ones. Now it's recommended to use channels 15, 20, and 25, 26 of Zigbee because, as you can see, they do not interfere with these popular channels within Wi-Fi. But our project is going to focus on minimizing the interference by being able to identify these the patterns in Zigbee and Wi-Fi from their spectrogram image, and being able to classify these two signals. And now we're going to set up the project, and the first thing we need to do is to generate the data, the synthetic data that we need in order to train our model on. So we're gonna head over to the steps on the project's GitHub page, and first we're gonna clone the project, go change our directory to the project, and we're gonna open MATLAB in that directory. And after that, after opening MATLAB, we have to go to scripts, data generation, and run generate data. So as of now, I'm in a WLAN Zigbee classifier. That's where you will end up by changing the directory to projects directory. And we're going to go to scripts, data generation, and generate data. And we're going to run this script. It's gonna take a while, so I'm gonna put a pause on video here, and I'll get back when I'll get back to you when it's done. So it took around 6.5 minutes for all the data to be generated, and we can find it in a directory called data in our main directory, the WLAN Zigbee classifier. And if we open it, we can see that they're stored in a 256 in 256 pixels folder. And for example, let's take a look at the WLAN PNG. So this is the spectrogram that we sent through, and this is the this is its label. So we give this image to the model alongside with its labels, and we say that, okay, in this image these pixels correspond to a WLAN, and that's how basically our AI model gets trained. We do that for WLAN frames, and here in this folder we have a combination of WLAN and Zigbee both together, their coexistence alongside their labels. And we also have Zigbee at the bottom here after WLAN. We also have Zigbee, so only Zigbee. Let me show you an example of Zigbee as well. So that's its PNG, and this is its labels. And let me find a better example as well. Maybe one, yeah, this one looks better. So we can see that it only labels that main part, so that 2 megahertz that of bandwidth that we talked about earlier, and we can see that they're correctly labeled. This is done using this function, WLAN Zigbee training data generator, which we can find in functions and in signal generation. This file here. So it basically generates training data with Zigbee WLAN signals and their combinations. And for example, if we take a look at the code, here it generates Zigbee only, here it generates WLAN only, and here, let me find it. And here in this part, it generates WLAN and Zigbee coexistence images that are stored in WLAN underscore Zigbee signals. This file utilizes Zigbee signal generator, which solely generates Zigbee signal, and WLAN signal generator, as well as and all these files utilize multipath channel for Zigbee for WLAN, and also they use the image processing functions in this directory, so saving pixel labels and saving spectrograms and so on. Now that we have the data, we'll move on to training our model on this data. So we're gonna move to scripts again, train model, and here we will run this train model script. This is going to take a while as well, so I'm gonna pause the video again here and get back to you when it's done. Okay, now the training is done, and it took around 1 hour and 40 minutes. So it will be saved in the directory called models, and it's the latest model. When you train an AI model, the latest one will be saved in train model. So basically these two models are currently the same. So now we have to test our model using Adam Pluto. In order to do that, we have to go to scripts, testing, and we have to first initialize our Adam Pluto SDR. So I'm quickly gonna show you how to connect SDR to your laptop, connecting the antennas, and I will come back and run this script, and then we're gonna run test with SDR and also generate some signals, generate WLAN and generate Zigbee, and see how the prediction works. So this is how Adam Pluto is connected to the computer. The covers have come out from the RX and TX, and the antennas are attached, and the Adam Pluto itself is blinking and is connected to the computer. And before I continue, I want to say a big thank you to Matt Ven, who helped me get the Adam Pluto SDR. That support made this project possible. Now, after connecting the SDR to the laptop, we will run this script, initialize SDR, and it's completed, and then we go ahead and test it. But before doing that, I don't have a Zigbee device by me, so what we're gonna do is that we're gonna generate Zigbee signal using MATLAB again, and transmit it via the TX antenna of our Adam Pluto, and then receive it again, and then give it to the semantic segmentation model and see how it classifies. If it classifies correctly, the signal correctly, if it's Zigbee, does it show Zigbee? If it's WLAN, does it show WLAN? And in order to do that, we go to we open wireless waveform generator. Just gonna bring it up here so we can see it. So first let's test Zigbee. So this one, the standard that we mentioned earlier, is for Zigbee. We change samples per chip to 20, and then we tap on generate, and when it's generated we go to transmitted. We select Pluto, add on Pluto, and when it's done we put the center frequency at 2.4 gigahertz and we start transmitting it. So now it's being transmitted. We close that and we go to test with SDR and we go ahead and run that. This is establishing connection. Okay, we got the results here. I'm gonna bring it up and I'm just gonna full screen this. Okay, so this is the signal that we received that MATLAB generates, and this is the classification, and as we can see it's been classified correctly as a Zigbee, and then this picture goes to another step and the Zigbee band will be shown here, so we can see that Zigbee is being transmitted on 2.4 gigahertz. So the model has correctly identified the Zigbee pattern in the spectrogram. Now we're gonna move on and do it for WLAN. So we are gonna open the waveform generator again. So we're gonna stop this, gonna go to generator again, WLAN, and I'm gonna put the bandwidth to 20 megahertz. I'm gonna tap on generate, and then I'm gonna tap on transmitting, add in Pluto 2.4 gigahertz and tap on transmit. Now it's being transmitted and we run our test with SDR once more. So the same script but with different signal being transmitted. Okay, so here is what it's identified. So this is WLAN, and it's mostly correctly identified all the WLAN signal, and it's just these parts that have been classified as Zigbee, which is an error, but overall it gives us a good view of what signal is being transmitted. So we said that the center frequency was 2.4 gigahertz and over a 20 megahertz bandwidth, so 10 megahertz to the right and 10 megahertz to the left is being classified very, very closely right. As a final example, I thought about doing it without transmitting anything to see if there is no signal. Does it correctly identify that? Does it classify any signal within there for WLAN or Zigbee? So I'm not transmitting anything at 2.4 gigahertz at the moment, and as you can see, it does not classify anything which is a correct behavior. It classifies everything as background or noise, which is expected. And last but not least, thank you for watching this video. I hope you've enjoyed it. See you later.